So we discussed about how orbital mechanics work in a nutshell. Now we're going to look at the elliptical orbit versus circular orbit. Elliptical orbit can be made by increasing the velocity at one point in a circular orbit, meaning that if there's Earth and you're spinning around, but you increase the velocity by a certain amount, then it will result in increasing the apogee, which is the highest point in this orbit, since even a circular orbit can't be 100% perfect. Like, this R and this R can't be perfectly, the same. So there's going to be a highest point inevitably. We call this an apogee. And if we increase the velocity here, it will increase the apogee like that. So this is called an elliptical orbit. And this is called a circular orbit. This can be all explained by Kepler's third law, but we're going to go in depth in that topic a little bit later after we understand the conservation of energy in both circular and elliptical orbits. So before we go into math, we're gonna just try to make a pseudo calculation of the energy that the spacecraft possesses at different points in the circular orbit and the elliptical orbit. So let's say the spacecraft is here at the apogee in the elliptical orbit. Well, let's look at the circular orbit first because that's easier. Let's set up 4 points in this orbit. According to the conservation of energy, the sum of potential energy plus kinetic energy, in this case there is no external force influencing the spacecraft's orbit. So we're just going to say this is potential energy plus kinetic energy. Same thing, potential energy plus kinetic energy. And here, potential energy plus kinetic energy. And here, it's also potential energy plus kinetic energy. The law of conservation of energy proves that these values are all going to be the same. It's just like an object dropping from an angular surface, but the energy is going to be conserved. Same thing, potential energy plus kinetic energy equals to potential energy of kinetic energy at this point, equals to potential energy plus kinetic energy at this point, equals to potential energy plus kinetic energy at this point. Things get a little more difficult when it comes to elliptical orbit. And I mentioned an angular surface is a little bit similar to what happens there. Now let's explore it. I'm just going to erase the circular orbit completely because we don't really need it right now. Now we're going to look at the elliptical orbit. Let's set up 4 points, just like what we did before. Here, it's a little different. So I previously mentioned that this, according to Kepler's third law, and as I mentioned before, the spacecraft won't just stay at the same velocity throughout the whole course, since in order to transition from a circular orbit to elliptical orbit, we gave a little boost in the velocity at the lowest point in the orbit, because that's the most efficient way to increase the altitude of the highest point. Altitude in this case is the distance between the surface and this highest point. So, and the highest point is also called an apogee. So if we give a little boost, it goes faster in this area, this low Earth orbit area, per se. So it goes like, but in this area, the velocity actually doesn't increase. It actually goes slower. But when you enter the region where it is closer to the surface of the Earth, it goes faster. So it goes kind of like this. So here, since the rocket goes faster, the kinetic energy is going to be big. The kinetic energy is going to be a big value, but the potential energy, since the altitude, the distance between the surface and this specific point is low, the potential energy is going to be small. Because we did learn that potential energy equals to mgh, meaning that depending on the height, the potential energy is going to vary. And in this case, this height is way smaller compared to this height. So the potential energy here is going to be smaller. So smaller potential energy. So let's keep it simple. Kinetic energy plus potential energy. Kinetic energy is going to be a big value. Potential energy is going to be a small value, since the potential energy at this point is small. But the kinetic energy is fast, because think about the formula. It's 1/2 mv squared, which is the value of kinetic energy. So depending on the value of velocity, kinetic energy is going to vary. It's going to be directly proportional, just like height being directly proportional to the potential energy. Therefore, since the spacecraft is going fast in this region, think about a bucket. it needs significantly more energy to spin a marble around the bucket when it's closer to the bottom of the bucket. It's hard to visualize, but you should try it. It definitely helps. So kinetic energy plus small potential energy. But let's compare it to this point. This point, the height is bigger, meaning that there's more potential energy. But as I mentioned before, the spacecraft is going to be inevitably slower in this region, where the altitude is higher. So the potential energy is going to be big, but the kinetic energy, since the velocity of the spacecraft in this region is going to be lower, the kinetic energy is going to be a small value. So compare this value to this value. Sure, the value of the kinetic energy and potential energy are different, but if we write it down, plus big potential energy, which is this point, equals to, this point's going to be big kinetic energy plus small potential energy. See how it kind of cancels out. So small kinetic energy plus big potential energy equals to big kinetic energy plus small potential energy. You notice that when one thing is big, the other is small. Same goes for this point. So it kind of cancels out and it becomes the same value. And this is how law of conservation of energy works in a circular orbit and an elliptical orbit.